Hello, I'm Hayeon Lee. Today I will present Transferable Neural Architecture Search with Diffusion model for the real world. Let's get started. The recent success of large foundation models has opened up the era of artificial general intelligence, AGIs, and AGIs are on par with human capability. Recent foundation models, like large language models, are learned on a massive data set to improve their generalization capability, and then they are adapted to various downstream tasks rapidly with the fine-tuning. They show impressive generalization capability on various tasks like natural language understanding, visual understanding, and code generation. From the success of foundation model, we have learned the importance of generalization capability of AI model to build successful AI system for the real world. In the AGI era, neural architecture search NAS technology also should have generalization capability while enabling fast adaptation to diverse downstream tasks. Then let's briefly review the current state of NAS. NAS goal, you might know, is to automatically design the optimal architecture for a given task. For this, usually we first define the search space, that is a set of possible neural architectures that we can design. It is usually very extensive, so we need an effective and efficient architecture search strategy. There have been many existing NAS methods. Early NAS methods use reinforcement learning to propose hyperparameter for an optimal neural architecture using the accuracy as the reward. Evolutionary NAS method use evolutionary algorithm to search for the optimal architecture by applying mutation or crossover on the architectures. And recently, NAS method like DART use gradient-based optimization to jointly learn the architecture weighting parameter and model parameters. Like this, in the past few years, over 1,000 papers published since 2020. However, are we going to the right direction? For each task, most traditional NAS methods task specifically work by training a NAS model from scratch, rather than making NAS model task agnostically. So their training is too slow and computationally expensive. It often takes multiple GPU hours or even days per task. And definitely, this process hinders the user to use NAS method for their real-world task. Second, NAS method should generalize over diverse real-world data set. However, traditional NAS method usually overfit on a few benchmark data sets, such as ImageNet 1000 or the Cyper-10. Lastly, these days, many pre-trained neural architecture exist in open source platform, and they could be the data for the NAS framework. However, most traditional NAS methods never use them. Then how can we improve NAS models' generalization capability? Today, I introduce a transferable NAS method that improves the generalization capability of NAS models. It works like other foundation models. It has two stages, like training stage and adaptation stage. During the training stage, NAS model is trained on a large number of NAS tasks, and it is adapted to a target NAS task rapidly. Especially, I have mainly used the meta-learning approach that learns to generalize over a task distribution. These works are transferable NAS series. They have validated the effectiveness of the method successfully on various domains and tasks. In sum, transferable NAS share the core philosophy as below. First, we train a single NAS model to learn the generalization knowledge from many previous tasks. Second, we adapt the learned NAS model to various new tasks. Then, we can perform fast, computationally efficient, and effective search by using a transferable NAS models. And specifically, I will introduce 4 key transferable NAS work. The first is MetaD2A. It's a fast and compute-efficient NAS method, and it is generalized across various data sets. And second, HELP. It is a NAS model generalized across various hardware devices. And third, TANS. It is a search for a pre-trained network from the model view. And final work is Diffusion NAG. It is a predictor-guided neural architecture generative framework using diffusion model. I think that it can be a new paradigm to overcome the limitation of existing NAS method. And this is first work, MetaD2A. As I said, conventional NAS methods start to train a NAS model from scratch for a given data set. When the data set changes, they start NAS model training from scratch again. Therefore, their search cost increases linearly with the number of tasks. On the other hand, the search time complexity of the proposed MetaD2A is bigger one. Once training across multiple tasks, MetaD2A can instantly search neural architecture on a novel data set, so for the processes, this reduces the search cost on the target task significantly. To train MetaD2A model, there are source database that consist of multiple tasks. Each task in the source database consists of a data set and its high-performing architecture. Then our MetaD2A approach learns to generate the high-performing architecture from a data set over multiple tasks in the source database. For a novel data set, MetaD2A used the learned knowledge to generate optimal architecture. Specifically inspired by variational autoencoder, we have designed dataset to architecture generative model. The generative model learns to map a dataset to a latent vector in the latent space. One challenging point is how to encode a dataset as a single representation. For this, we introduce a novel hierarchical set encoder. We use attention-based network as the encoding module. The proposed set encoder consists of 2 stages. At the first stage, it captures class information by intra-class interaction between the example within the class, and then it conducts the inter-class interaction between classes to encode the dataset as a single representation. The generative model decodes the latent vector as high-performing architecture with a decoder. We represent a neural architecture as directed acyclic graph. So, as an architecture decoder, we use the directed acyclic graph decoder. The generative model is learned over the source database. And during the search phase, our generative model can stochastically generate multiple high-performing architecture candidates from a single latent vector. We also introduce a dataset-aware accuracy predictor. There have been various conventional task-specific accuracy predictors in the NAS community. Usually, they collect a training sample consisting of a neural architecture and its actual accuracy pair. To get actual accuracy pair, we need to train each neural architecture on a target dataset. We train accuracy model on collected training sample. Then, we can use the trained predictor during the search process to evaluate unseen neural architecture in the search space. While the collecting training samples are very time-consuming, we need to repeat such a process when a dataset is changed. To overcome this limitation, the proposed dataset-aware accuracy predictor can conduct dataset condition accuracy predictor. That means that even for the same architecture, if datasets are different, our predictor predicts accuracy differently. For dataset condition accuracy prediction, similar with the generative model, we use a set encoder to encode the dataset as a single representation. Also, the predictor is trained over multiple datasets. So, by taking an unseen dataset and unseen neural architecture candidate generated by the generative model as input to the predictor can evaluate the architecture by predicting the final accuracy dataset conditionally. Then we pick the neural architecture that has the highest predicted accuracy as the final accuracy. In the searching phase, for the unseen dataset, we can deploy the learned generative model to generate architecture candidate, and the learned predictor pick the best one among them to output task-optimal neural architecture rapidly. This is end-to-end search result on 6 unseen datasets. Our model is trained over multiple tasks, and each task consists of the subset of ImageNet 1000 and architecture of NAS-Bench 201. We test it on unseen dataset without direct NAS model training on that target dataset. And other baseline NAS models are trained directly on a target dataset. And as you can see, the proposed method outperforms other baseline. Also, since the proposed method D2A do not need to train on a target dataset, during the search phase, it just needs a few GPU seconds as the search time. And in the figure 1, we visualize the latent embedding generated by the generative model. And we can observe that the generative model classifies well embeddings of unseen dataset in the latent space, while cluster the latent vector of the subset of the same dataset. The figure 2 shows the quality of the generative architecture. The generative model sampled 2,000 architecture candidates from the embedding, encoded each target dataset, and compute the validated accuracy of those architectures. The proposed generative model generates more high-performing architecture than the simple random architecture sampler for each target dataset. And this shows that our generative model allows us to effective and efficient search by excluding the poor-performing architecture of a broad search space. And this is my second work help, hardware adaptive efficient latency predictor for NAS via meta learning. Hardware-aware NAS, its goal is to provide an optimal neural architecture under the device-specific constraint. Usually, we consider latency as an objective. Most hardware-aware NAS methods have focused on designing a neural architecture that have a good balance between accuracy and latency. During the search process, many NAS methods have used a latency predictor that can predict inference latency of unseen architecture on a target device without directly installing it on the device. However, to build a reliable latency predictor, we need at least a few thousand latency data samples for various architectures measured on each hardware device. However, collecting such data is a big obstacle for using hardware-aware NAS method in the real world. Installing a collection pipeline is complicated, and collecting thousands of data takes a lot of time. For example, for mobile phone, we need to implement application and install it to the phone physically to collect sample. Such process can be a main bottleneck to use NAS method. On the other hand, the proposed hardware adaptive latency predictor adapts to a new device using only about 10 data samples, and then accurately predict the latency for unseen architecture on the device. We learn the latency predictor to work well on different unseen devices using knowledge learned from other previous NAS tasks. The key challenge is how to make one single predictor learn how to work on many devices, no matter what kinds of hardware type they have. Therefore, we propose a hardware condition predictor by encoding the device as a representation, embeddings, and taking it as the condition. However, a challenging point is that representing a hardware device is not easy. Each device has a unique physical structure and hardware platform. So our idea is simple. We treat each device as a black box function and prepare fixed reference architecture and measure their latency on the target device and use the latency set on the reference architecture as the device embedding. To train the proposed latency predictor, we adopt the model-agnostic meta-learning scheme called MEMR. MEMR score is to find an initialization parameter that can be quickly adapted to a new task via a few gradient steps. We perform MEMR-like meta-learning of a single latency predictor by learning it over multiple tasks to generalize to unseen device. Help perform hardware-aware latency predictor for a neural architecture by taking both hardware embedding and a target neural architecture as the input. Furthermore, we introduce a hardware adaptive modulator JET. When we encounter with a completely new device, it can be considered as out of distribution task, and it will be helpful to deviate more from meta-knowledge captured by the initial parameter. In this case, the JET modulator is multiplied with the initialization parameter, zeta, to make the model deviate from the meta-knowledge. This is possible by the JET modulator is predicted hardware adaptively for each hardware. Usually, JET modulator modulates the initial parameter to be closer to random parameter if the meta-knowledge is not helpful. Similar with MEMR, help meta run a few-shot regression model from training pool and perform a few-shot adaptation with a few-shot sample collected from the target device. To validate the proposed method, we collect latency measurement from 17 heterogeneous devices. In the meta-training pool, we use GPU, CPU, and mobile phones. We construct meta-training pool with devices that are relatively easy to collect sample by considering realistic scenario. In the meta-test pool, we consider two categories. The first category is unseen device, and the second category is unseen platform. Unseen device is different on the device in the meta-training pool, but belong to the same category of the meta-training pool. Unseen platform is completely unseen category of a device like ASIC, FPGA, Raspberry Pi, and Edge GPU. To validate the proposed method, we compute Spearman's length correlation coefficient between latency estimated by the predictor and actual latency measured on 6 unseen devices and unseen platform. And as you can see in the table, the proposed model is highly sample efficient. With just 10 training samples, the proposed model outperforms state-of-the-art model using 3,200 training samples on 6 unseen devices. And this is visualization result. Figures visualize correlation between estimated and measured latency on a Titan RTX GPU and Intel Xeon Gold CPU. The proposed meta latency predictor requires only 10 samples for adaptation and outperform it in the estimation performance. And in the figure 1, we can observe that as the number of training samples increase, the proposed method is more effective compared with existing meta-running method and existing latency predictor. In the figure 2, we empirically observed that Regardless of hardware type, it is sufficient to use a moderate number of devices, in our case is 8, as a meta-training pool for meta-learning. Finally, when we coupled with a rapid NAS method like one-for-all, help can remove the bottleneck to collect training sample, we can perform the entire latency constraint NAS process for a new device within minutes. And this is my second work, task adaptive neural network search with meta-contrastive learning. Recently, we can find lots of free models already trained on various datasets in open source platforms like GitHub or Hugging Face. However, traditional NAS methods usually do not leverage a model view containing numerous pre-trained models. Instead, they start the search process from scratch and only focus on finding neural architectures rather than the parameter. Then what if we could find a pre-trained network that is optimal for our dataset and condition from an open source model platform? For this, we introduced a new problem called neural network search, NNS. Its goal is to retrieve the best pre-trained network for a specific dataset and condition. To address such challenge, we newly introduced the novel method, namely task adaptive neural network search. TANS. TANS consists of several components: efficient model view construction, and model and query encoder, performance predictor, and meta-contrastive learning framework. First, we construct a model view to simulate our open source platform. It contains more than 15,000 pairs of models trained on diverse real-world datasets collected from Kaggle. The model view includes various datasets like face dataset, medical image dataset, and fine-grained dataset. In this work, we perform a pre-trained network search in cross-modal latent space between pre-trained model and dataset. So, to encode a pre-trained model into a model embedding, we designed the model encoder. For encoding a neural architecture, we simply represent operation as a one-hot encoding. And to encode model parameter, we consider a model as a function. So the model takes a single criterion generated from a Gaussian distribution as input, and the model's output is considered as an embedding of the model parameter. We can call this as a functional embedding. By taking architecture embedding and functional embedding as input to model encoder and output a final model embedding. To encode a dataset called query, we design simple pooling-based set encoder as our query encoder. So it can produce a query representation embedding. Similar with the set encoder that we introduced in our first work, MetaD2A, the query encoder encodes the entire dataset to a single query embedding. Putting model and query encoder and accuracy predictor all together, we perform meta-contrastive learning to learn the cross-modal retrieval space. In the latent space, the proposed algorithm maximizes the distance of irrelevant pre-trained model embedding and the dataset query embedding. And the proposed framework minimizes the matched the pre-trained model embedding and query embedding pairs. Now, we have a model view and learn a model encoder, query encoder, and the predictor. In the search page, let's assume we have our query dataset and constraint and want to find an appropriate pre-trained network for our dataset constraint from the model view. For this, our pre-trained network from the model view are already encoded as latent embeddings by the model encoder. The query dataset is encoded using the query encoder. Then we compute the cosine similarity between the query embedding and the embeddings of pre-trained networks and retrieve n network candidate with high similarity with the query embedding. Finally, the predictor is used to select the final pre-trained model from the network candidate pool. This is experimental result, and in this experiment, we report the average performance of searched network on 10 unseen real-world dataset crawled from Kaggle. The baseline model are existing NAS method, and some of obtained a neural architecture is pre-trained on ImageNet 1000 and fine-tune a target dataset. And as you can see in the table, TANS outperform our baseline, and we think one of the reasons is that TANS retrieved the model pre-trained on a relevant dataset with the target dataset. As shown in the figure, we also compare the performance of TANS with the real AUTOML platform of Microsoft Custom Vision and Google's Vision Edge, and TANS show shorter search time and better performance successfully. And this image shows the relationship between the query dataset and dataset used for pre-training the retrieved model. In most cases, the proposed method matches semantically similar dataset to the query dataset. Yes, and this is my last work, Diffusion NAG, test-guided neural architecture generation with diffusion model. In the first work, we introduced meta D2A, and in the meta D2A, the generative model generate dataset optimal neural architectures from dataset by using the prior knowledge. However, the meta D2A generative model has two limitations. First, it failed to explicitly consider objective as a core condition for generating neural architecture. Instead of incorporating objective, meta D2A simply relies on a dataset as a single condition during the generation process. Furthermore, meta D2A uses a predictor only to sort and select neural architecture based on their predicted performance. However, if the predictor does not actively participate in the architecture generation process, it can lead to suboptimal result. To overcome this limitation, we use diffusion models. Recently, they have shown impressive high generative capability across diverse domains like images, molecular, and speech generations. Diffusion model consists of a forward process and a reverse process. During the forward process, it diffuses the data to noise by adding noise progressively and learn to reverse the process to generate data from the noise. The strength of diffusion model is its conditional generative capability. We can apply the guidance scheme to the diffusion model. The guidance scheme allows the diffusion model to condition on a desert property. Gradients from the classifier or predictor are used to guide the generated sample toward the desert property. For example, during the generation process, as shown in the left figure, classifier's gradient steer image sample to match a label. And as shown in the right figure, the molecular property predictor, its gradient guide the discovery of novel and chemically meaningful molecules. Inspired by them, we propose diffusion NAG, our diffusion model that can generate a neural architecture within the search space from a noise. We also use the guidance of the performance predictor to allow the diffusion model to condition on an objective like accuracy or robustness to generate architecture. Diffusion NAG framework consists of 3 distinct stages. In the first stage, the score network learns an unconditional neural architecture generation process. And this process involves generating neural architectures following an architecture distribution. Usually, architecture distribution means the search space. And to achieve this, we define a forward diffusion process where the neural architecture distribution is perturbed to a non-prior distribution like Gaussian normal distribution. And then we learn the score network to reverse the perturbation process to sample architecture from the search space, starting from a random noise input. However, generating random architecture from the entire search space is not sufficient. This is because our goal is to generate optimal architectures that satisfy an objective rather than generating random architecture. So we need to perform conditional generation to generate neural architecture that meet the desired property. For example, if we consider accuracy as our objective, we should generate architecture that have high accuracy rather than random architectures. Therefore, as the second step, we guide architecture generation toward maximizing the predicted accuracy using the gradient of dataset-aware predictor. Following Yang Song's work, score-based generative modeling, the stochastic differential equation, the conditional architecture generation process can be estimated with a sum of a score network and the gradient of predictor to predict architecture's performance on the objectives. The score network is independent of the objective, and it is only dependent on the architecture. So this means within the same search space, we can share the score network across various tasks. And that means by changing the type of predictor depending on the goal that we achieve, we can do an objective conditional neural architecture generation. If our goal is to get architecture that has high accuracy, then we can use the predictor trained to predict the accuracy. Or if our goal is to get architecture that has robustness, accuracy against being attacked, then we can use the predictor trained to predict accuracy after being attacked. Diffusion NAG is also transferable within the same search space, as I said, and if we combine diffusion NAG with the MetaLearn dataset-aware predictor designed by MetaD2A, it is also transferable across search space and dataset. This is an experimental result, and to validate our framework, we generate 1,000 architecture using random architecture sampling, and MetaD2A is our main baseline. Then we analyze the distribution of generated and sampling architecture. And as you can see, our model generates a higher proportion of high-performing architecture compared to other methods by effectively restricting the search space to exclude poor-performing architectures. And to emphasize the significance of our conditional diffusion framework, we perform an experiment that we conditionally generate 10,000 architecture using our diffusion model, and then we employ the predictor to select the top 1,000 architecture rather than using guidance scheme, just simple using sorting and selecting scheme. The result in the figure clearly demonstrates that our conditional generation approach surpassed the unconditional approach, highlighting the necessity of our condition framework. And we also compare our diffusion NAG with various NAS methods on 4 unseen datasets. Our results highlight 2 key findings. Firstly, architecture generated by diffusion NAG consistently outperform our baseline across our dataset, and it reduced the search cost by minimizing the number of architecture that need to be trained to achieve high performance. Unlike existing NAS methods that explore the best search space, our approach leverages prior knowledge from the predictor. And our system, our framework, can easily adapt it to new tasks by changing the predictor without having to retrain the score network, as I said. To validate it, we train 3 predictors for different purposes, one for regular accuracy, and one for architecture after APGD attack, and one for accuracy after block corruption. Using this predictor as guidance, we made a group of 20 different neural architectures. We checked how well this architecture performed on different tasks like regular accuracy and APGD attack and block corruption, and we found that architecture made with a predictor specifically trained for a task did better on that task. For example, architecture made with a regular accuracy predictor did not do well against attack and blurry image, but those made with predictor for attack and blur did much better on those tasks. This showed that our framework can work well for different goals, I think. And lastly, we have shown that by incorporating diffusion log framework instead of a heuristic optimization strategy like random sampling, random architecture sampling, or mutating architecture in the Bayesian optimization-based NAS, we can improve the performance of such a BO-based NAS method. I skipped the details of BO-NAS algorithm, but the main algorithm is of BO-NAS is that we usually use an iterative algorithm, and at each iteration, we expand the population of obtained architectures. To do this, we either randomly select new architectures or mutate existing architecture to create a new architecture candidate. We then use a predictor to pick the architecture that maximizes the acquisition function, and we add this architecture to our existing population. We repeatedly perform such iterations. And during this BO loop, instead of using random architecture sampling or mutation technique to choose new architecture candidate and make prediction with a predictor, we observed that using the architecture candidate generated by the diffusion model method can improve the performance of BO-NAS. Especially at the early stage, we observed that using the diffusion log method is more effective. In BO-NAS, the predictor is retrained every time the population is updated, is retrained on that population. And at the early stage, the predictor may not perform well when the population size is small, so there are few training samples in the population. However, we observed that diffusion log is relatively robust the performance of the predictor compared with the method that used the predictor only for sorting and selecting architecture. Yeah, thank you.
Thank you for that wonderful talk. Does the crowd have any questions?
Thank you very much. Very awesome. Definitely. I wanted to ask about the last part about generation of the architectures and combining that with BO. Can you still guarantee that it can find in principle all kinds of architectures, or is that somehow limited then by this generation process?
Your question means, can we guarantee to generate all architecture in the search space?
Yes.
Yes. In the case of unconditional diffusion log, it can generate. I think it can guarantee to generate new architectures in the search space. But our interesting part is to generate a good architecture for our task. Yeah. So. Yeah.
Good. Thank you.
just not throw it and hit Frank.
Yeah, thanks for the talk. Really interesting work. Also had a question for the last plots. So I guess I don't know, like, what is you said that you refit your model every iteration to the new add. So when you add in the BO loop one new configuration, you fit your model again, right?
Sorry, pardon?
When you add one new architecture to the population, you refit the model every time, right?
Right, yeah.
How long does that? Is it expensive to do that refitting?
Within few GPU minutes, we can generate 100 of architecture. Oh, sorry. Yeah. Generation process is not much computation expensive because within just few GPU minutes, we can generate 100 of architectures. So I think compared with usual search cost, it's relatively cheap, I think. Yeah.
Okay. Yeah, I meant more about refitting. So do you train the model always when you add new members to the population?
You mean train or architectures?
Yeah. So train the generative model, I mean.
No. Following the BO loop, we just only for few or one picked architecture, we train them only. And
okay.
yeah,
So you fine tune on the new.
Yeah, or architecture.
Okay.
We did not train all them. We
Okay.
just predict their accuracy by using the predictor.
Okay, yeah. So I was just wondering how it will look on the runtime on the x-axis, like, and not on trained architecture. That's why. But
Yeah, and so the x-axis means the number of architecture.
yeah.
Really trained.
Yeah, I was just wondering if you had wall clock time on the x-axis. Like, that's why I asked how expensive it is to retrain the model.
Real time.
Yeah.
I think it's depending on the search space or architecture type.
Yeah.
So if we use the benchmark like NAS bench 201, in that case for each architecture just within 2 hours for each architecture. And this search space, in this case, it is more larger architecture in the search space. So we need more time than 2 hours for each architecture.
Okay. Yeah. Thanks. Yeah.
Thank you. Amazing talk. I was wondering, how well do you think that these methods will transfer to new domains? So that's how, if you do meta learning, you learn a specific distribution of tasks, right?
Right.
What if you have a new task out of the distribution? How well do you think your methods would be able to adapt to find models for new kinds of tasks that you haven't seen before, outside of your distribution? No?
Can you explain again? Sorry.
Okay, so you learn for a number of tasks, you meta-learn this search space, right?
Yeah.
What happens if you try to adapt to a task that's very different from the ones you've trained on?
You mean the size of meta training task, or?
Yeah.
It depends on the work. For the first work, meta D2, and the last work, diffusion knock model. To train a model, we collect 5,000 tasks. Yeah, and for the hardware awareness, in that case, I forgot the specific number of tasks, but it's under the 1,000 task.
Okay, and they all transfer well, I guess. No? Okay, so I want to clarify. So say you train on all of ImageNet, right? And now you get a model that's very specific, like a radar, a chest radar, or whatever, like a medical data set. which is very different.
You mean the coverage of meta test?
Mm-hmm.
Meta test task? Except for the third work times, actually we just test on natural image data set, and for the times we use medical data set and other real world data set as a test data set.
All right, cool.
Yeah.
All right, thank you.
All right, can we do an online question?
Yeah.
Yes. So Ilya online asks, how does general AI fit into this? Also, do you have plans to share code of all of this?
Code or data set? Sharing code?
I believe code, yes.
Except for the diffusion log, because it's under reviewing. Other three work, already code is open in my GitHub. Yeah.
And then I guess the other question was, how does general AI fit into this? I'm not sure what general AI means. But interpret it as you may.
Yeah. The ultimate goal that I want to achieve is a single NAS framework can support many real-world tasks. For example, if we build our company, then our single platform can support task-optimal neural architecture to the customer's data set. Yeah. But yeah, there is a lot of steps to do so.
Can I ask a question? Okay. So first, thank you for the very interesting talk. I have one question regarding the diffusion model. What type of diffusion model are you using? Because normally we use diffusion model to only generate the continuous samples. But for new architectures, we always have the discrete search space. So do we have to do anything with the diffusion model?
Yeah, that is a very good question. And I did not refer the specific paper in this presentation, but I used continuous time diffusion model for graph generation. Yeah, I adapted that work to our model. So we perform to generating graph in the continuous field domain, and convert continuous things to discrete graph. Is it your question correct? Am I understand correct?
Yes, thank you. I'm wondering because the different operation do not have exact order. Like we say, the operation 1 cannot be smaller than operation 2, or the distance between operation 1 and 2 cannot be larger than distance between operation 1 and 3, because normally we do one-hot encoding for this type of operations or data.
Yeah. We tested our model on 2 search space, and they have different operation type. And for the small case, just 5 operation type. We can handle it, and in this mobile net version 3 search space, in this case, we can handle 20 operation types. Yeah, we identify it. And I think more larger search space and more complicated architecture, we think a diffusion model can handle it. Yeah.
Okay, thanks.
Hi, very interesting talk. So I had a question about if you have, so the way I understand it, for diffusion NAG, it's very much dependent on the search space, right? So you train a separate diffusion model for every search space. So that there's a cost involved. So have you thought about how you would generalize across search spaces, or like use a single diffusion model for multiple spaces?
This is a very good question. Yeah. Until now, this version is trained on each search space. So as you said, if the search space is changed, we need to train the score model again. But we think one or possible future work is beyond the rigid fixed search space. That means this is generation framework, so we think it can possible to expand or change the search space, or it can generate the new architecture beyond the already fixed search space. In that case, one score network can support various architecture type, yeah, and so on.
Mm-hmm. Yeah, thank you.
Thanks. Great talk. I have one question for the help paper. You introduced a hardware adaptive modulator that is also parameterized. How did you train that?
Yes, you mean this, right?
Exactly.
Yes, as you said, modulator jet is also kinds of parameterized model, and so we need to train it. And we train it with the hardware-aware latency predictor help together during the meta training. And if you want to see more details, you can refer one of my other work, learning to balance. Yeah, in that paper, we explain more about such task-specific balancing variables like jet modulator. So it is just focused on the meta learning. So you can refer it. Yeah.
Perfect. Thanks.
For more detail.
Are there any more questions?
Thanks for the great talk. I think this help method also beautifully connects to the talk of this morning, right? You could consider this as a kind of collaborative filtering task. What kind of model did you use here to make predictions for new hardware? So you had these two embeddings, right? For hardware and for architectures.
Yes.
And then you could also span a matrix over these two, right?
Yes. And
what kind of predictor did you use to make then an informed guess based on these embeddings here?
What kinds of
or is
predictor
it just
model?
this modulator here?
Yes.
Okay.
For the modulator, we also have another type of set encoder. And yeah, you also read my other paper, Learning to Balance. In the paper, yeah, details are in the paper. And for the latency predictor, we just use simple MLP, multi-layer perceptron. Yeah,
okay.
it's enough. Yeah.
Okay.
I think more complicated model can better performance, but in our case, it's enough. Yeah, it worked well.
Okay, thank you.
Okay, please give a round of applause for Hayeon for a wonderful talk.